Hi, I'm Andreas and I will present our work iPOKE, poking a still image for controlled stochastic video synthesis. This is joint work with Timo Milbich, Dorkenwald and Björn Ommer. How would a static scene react to a local poke? On the one hand, there will be defined movement of the poked part and the closely related ones. On the other hand, the remaining object parts will obtain stochastic motion variations governed by the object's kinematics. Can we teach an artificial visual system to obtain this twofold understanding? Existing approaches lack this, as they either deterministically generate plausible responses to control inputs, or present conditional probabilistic frameworks for stochastic synthesis with no means for precise local control of the object motion. To bridge this gap, we present iPOKE, a conditional probabilistic model to enable controlled stochastic video synthesis based on local control inputs such as simple mouse drags. Our model is conditioned on a still image frame and a local control input and learns a stochastic kinematics representation to model the inherent ambiguity in the motion of the remaining object parts. Thus, our conditional probabilistic video generator enables local specification of intended object motion while simultaneously generating diverse movement of the remaining object parts. It is not only the first model to achieve a both controlled and stochastic video synthesis, but also enables human users to animate still images based on simple mouse drags and can be learned from unlabeled videos for arbitrary object classes. The standard approach for learning conditional probabilistic video models is a conditional variational autoencoder, which employs strong regularization constraints to obtain a stochastic motion representation. Such approaches, however, buy the stochasticity at the cost of visual and temporal quality due to the information bottleneck implemented by the regularization constraint, which contradicts the additional reconstruction objective. To avoid this, we divide the problem and first learn an autoencoder with no regularization constraints, which is capable of high fidelity reconstruction of videos X based on a compact spatial video representation Z. Next, we train a conditional generative model realized as a conditional convolutional normalizing flow. Our goal is here to establish a conditionally bijective mapping between Z and the normally distributed variable R. We train our model by minimizing the Kullback-Leibler divergence between the distribution defined by the inverse mapping and the standard normal, which can be shown to be an upper bound on the mutual information between the variable R and the conditioning. Thus, a minimizer not only yields a conditional generative model, but also ensures independence of R from the start frame and the control input. Thus, R indeed only encodes the residual kinematics of the remaining object parts. Contrasting CVIE-based methods, our approach has no contradicting loss terms and thus faces no trade-off between capturing all the remaining data variations beyond user control and the visual quality of generated samples. To obtain control inputs for training, we estimate optical flow between the start and end frame of each training sequence and, assuming a static background, randomly sample an object part with sufficient amount of motion. As a result, our model can be learned from unlabeled videos and is applicable to arbitrary object classes as we are not bound to parametric shape representations such as key points. During inference, we randomly sample R from the standard normal and apply the forward mapping conditioned on a still image x0 and the user control C to produce a video code Z, which results in a plausible object response to C. Thus, iPOKE enables human users to animate static images with simple mouse drags. Here we show examples of our model for the object class of humans. Each row shows a ground truth video sequence followed by samples from a residual kinematics representation for the control input defined by the red arrow and the start frame of the corresponding ground truth video. Our model generates diverse videos which nonetheless all show movements of the controlled body part to the desired endpoint indicated by the red dots. As our model can be learned from unlabeled videos and does not require parametric shape representations, we can learn it for arbitrary object classes. Here we generate plant motion. iPOKE outperforms the CVIE-based state-of-the-art models in stochastic video synthesis in terms of visual and temporal quality as measured by the FVD score, as well as diversity, as it does not face the trade-off exhibited by variational approaches. This can also be seen qualitatively. Moreover, our model outperforms the recent methods for controlled video synthesis in terms of FVD and also improves controllability as indicated by the lower LPIP scores. For details concerning quantitative evaluation, please refer to our paper. As the kinematics representation is independent of both object appearance and the control input, it enables kinematics transfer between two different instances of the same object class. Here, we use the inverse mapping to infer kinematics R from the sequence in the top row and transfer it to the persons in the second row by using the forward mapping conditioned on their respective appearance. The last row shows results for the same scenario with non-inferred random kinematic samples from R. To see further results of our model and much more applications, read the paper or visit our project page. We also present a graphical user interface where you can directly test our model, clone the code and get in touch with it. Thanks for your interest.